Hello! In today's video, we're diving into a powerful topic in precalculus: parametrizing implicitly defined functions. By the end of this lesson, you will be able to represent a curve in the plane using parametric equations, and you'll be able to parametrize conic sections like parabolas, ellipses, and hyperbolas. So, what are parametric equations? Think of them as a set of instructions that tell you where to be at any given moment. Instead of a single equation relating x and y, we have two equations, one for x and one for y, that are both defined by a third variable called the parameter. We'll typically use the letter t for our parameter. When we have an implicit function, like x squared plus y squared equals 25 for a circle, the parametrization we create must satisfy that original equation for every single value of our parameter, t. Let's make that idea concrete with a simple example. Our first objective is to represent a curve in the plane parametrically. We'll start with the most straightforward case, a function where y can be explicitly written in terms of x. Consider the function f of x equals 2x squared plus 1. If you're asked to find a parametric representation for this, there's a very simple and reliable strategy. You let the parameter t represent x. We simply set x equal to t. Once we've done that, the equation for y follows directly. We substitute t for x in the original function. So if y equals 2x squared plus 1, it must also equal 2t squared plus 1. This gives us our parametrization. X equals t and y equals 2t squared plus 1. This means for any real value of t we choose, we can find a corresponding xy point that lies on the parabola y equals 2x squared plus 1. To show you this works, let's pick a value for t. Say t equals negative 2. If t is negative 2, then x is negative 2, and y is 2 times negative 2 squared plus 1, which is 9, so the point minus 2, 9 is on our curve. Let's check this in the original equation. Is 9 equal to 2 times negative 2 squared plus 1? Yes, it is. This confirms that our parametric equations correctly trace the curve. The parametrization, x equals t, y equals f of t, is a general method you can always use. Next, let's explore how to parametrize functions that are invertible. Our objective here is to connect the parametrization of a function with its inverse. If we have a function, y equals f of x, we've just seen that its parametrization is x equals t, y equals f of t. Let's call this the original parametrization. Now, think about what an inverse function does. It swaps the roles of x and y. So, it makes sense that its parametrization would do the same. If y equals f of x is invertible, its inverse function's parametrization is found by swapping the x and y components of the original parametrization. The parametrization for the inverse is x equals f of t, y equals t. Let's demonstrate with an invertible function. Consider the function f of x equals the square root of x minus 1, but only for x greater than or equal to 1. The restriction is important because it makes the function invertible. A parametrization for f of x is x equals t, y equals the square root of t minus 1. To find the inverse function's parametrization, we simply swap these two. The parametrization for the inverse is x equals the square root of t minus 1, and y equals t. It's a direct consequence of the definition of an inverse. The parametrization of the inverse function has the x and y components swapped, compared to the original. Our next objective is to represent conic sections parametrically. Let's start with the parabola. A conic section we've already seen how to parametrize. We'll explore another common scenario. A parabola's parametrization depends on how the equation is oriented. If you can solve for y, like in our first example, you parametrize with x equals t. But what if you have an equation that's easier to solve for x? Consider the equation x equals y squared plus 2y plus 1. This is a parabola that opens to the right. Solving this for x is easy. In this case, it makes sense to set y equal to the parameter t. Let's work through this example step by step. We'll parametrize the parabola x equals y squared plus 2y plus 1. First, we set y equal to our parameter t. This is our choice to make the algebra simple. Second, we substitute t for y in the original equation for x. This gives us x equals t squared plus 2t plus 1. And that's it. Our parametrization is x equals t squared plus 2t plus 1, and y equals t. This method is incredibly flexible and works for any function you can solve for, either x or y. Now let's tackle the parametrization of an ellipse. Unlike parabolas, there isn't a simple set x equals t method here. We need a new strategy. We're looking for functions for x and y in terms of t that, when substituted into the standard form of an ellipse equation, will make the equation true for all t. The key insight comes from trigonometry. Think about the most fundamental trigonometric identity: sine squared plus cosine squared equals 1. This identity is the perfect tool for our ellipse. Let's rewrite our ellipse equation to match the form of the identity. We can move the a and b to the inside of the squares, like this. Now, notice the similarity. We can see that to satisfy this equation, we can make the first term equal to cosine squared of t, and the second term equal to sine squared of t. This gives us two equations: x minus h over a equals cosine of t, and y minus k over b equals sine of t. A little algebra solves for x and y. And there you have it, the standard parametric form for an ellipse. The parameter t, often called the angle, usually ranges from 0 to 2 pi to trace the entire curve once. The center of the ellipse is at h, k. Thanks for watching. Let's apply our parametrization formula to a specific ellipse. We'll parametrize the ellipse with the equation x squared over 4 plus y minus 1 squared over 9 equals 1. The goal is to identify h, k, a, and b. First, let's determine the center of the ellipse, which is the point, h, k. The h value comes from the x term. Since we just have x squared, h is 0. The k value comes from the y term. We have y minus 1 squared, so k is 1. The center is at 0. Now, let's find a and b. Remember that a is the half-length of the major or minor axis, and b is the other. The denominator under the x squared term is 4. That's a squared. So a is 2. The denominator under the y minus 1 squared term is 9. That's b squared. So b is 3. In this case, since b is larger, the ellipse is oriented vertically. Now we have all the pieces we need to write the parametric equations. Using our formula, x equals h plus a cosine t, and y equals k plus b sine t, we substitute our values. This gives us the final parametrization: x equals 2 cosine t, and y equals 1 plus 3 sine t. As before, the parameter t runs from 0 to 2 pi to complete one full trace of the ellipse. Our final objective is to parametrize a hyperbola. This is similar to the ellipse, but we need a different trigonometric identity. For hyperbolas, we turn to the identity secant squared of t minus tangent squared of t equals 1. You might remember this 1. This identity will be the foundation for our parametrization. There are two main cases for a hyperbola's orientation. First, a hyperbola that opens left and right. This happens when the x term is positive. The parametrization follows the identity. The x term gets the secant function, and the y term gets the tangent function. The domain for t needs to be adjusted slightly to avoid vertical asymptotes of secant and tangent, but 0 to 2 pi is often used to ensure both branches are covered. Second, a hyperbola that opens up and down. This happens when the y term is positive. The roles are swapped. The y term gets the secant and the x term gets the tangent. Let's work through an example of the first type. Let's apply our formula for a left and right opening hyperbola to a specific equation. Our task is to parameterize the hyperbola with the equation x squared over 16 minus y minus 2 squared over 9 equals 1. Our goal is to identify h, k, a, and b. Just like with the ellipse, we start by finding the center, h, k. From the x term, we can see h is 0. From the y term, y minus 2 squared, we get k is 2. The center of our hyperbola is at 0, 2. Next, let's find a and b. Be careful here. A squared is always the denominator under the positive term, and b squared is under the negative term. Since the x squared term is positive, a squared is 16, so a is 4. Since the y term is negative, b squared is 9, so b is 3. Now we have all the components to write our parametric equations. This hyperbola opens left and right, so we use the secant-tangent form. Plugging our values in, we get x equals 0 plus 4 secant t and y equals 2 plus 3 tangent t. The final parametrization is x equals 4 secant t and y equals 2 plus 3 tangent t. Remember that this parametrization will trace both branches of the hyperbola. So, let's quickly recap what we've learned today. We started by understanding that a parametrization represents a curve using a third parameter, usually t, which defines both x and y. The core principle is that the parametric equations must satisfy the original implicit equation. We learned a simple, universal trick. If you can solve for y, set x equals t. If you can solve for x, set y equals t. This works for any function, including parabolas. For conic sections, we turn to trigonometry. For an ellipse, the sine squared plus cosine squared equals 1 identity is our key. For a hyperbola, we use the secant squared minus tangent squared equals 1 identity, being careful to choose the correct form based on the hyperbola's orientation. The skill of expressing these equations in different forms is incredibly valuable, not just for understanding geometry, but also for advanced topics in physics and engineering. You are now equipped to take a given curve and represent it parametrically. Thank you for watching.